So in this talk, I'm probably just going to give you sort of a brief overview of the Assured Autonomy program. And mostly I'm sort of providing you some overview of why we started the program, what are the key challenges, what kinds of things we're working on, and then some of the challenge problems that we're looking at. Okay, so let me just sort of start with the obvious. Learning systems are essential for real-world autonomy. This is quite clear from the kinds of systems that we already see on the road. Some of the prototypical platforms that we work in DoD, which are sort of already to some extent in use, and in sort of planning and design and deployment stage. So the examples that are shown here are from three of our performers, Boeing, Northrop Grumman, and TARDEC or CCDC. And then they all have, some sort of application learning. And let me just state that I use learning sort of in a broad sense, but you could just think of that to imply machine learning based on neural network, typically as it's used in this context. And the applications for learning in a lot of these contexts are, at least as of now, are in the context of perception and some degree in control and planning as well. So that's sort of what's happening in the real world in the sense of use of learning and in achieving autonomy. That said, we all are aware that machine learning has its sort of own set of brittleness and opaqueness. I'm sure we've all seen our sets of panda and gibbon images where tweaking a few pixels end up getting a panda characterized as a gibbon and vice versa. Um, Now, if these kinds of brittleness or misclassifications are limited to web applications and classifications problems sort of in an abstract environment, then it's less of a concern. But when these techniques are used part of safety critical systems where a neural network may end up controlling where a spinning propeller heads or where a one-ton vehicle heads, then these issues become quite challenging and visual. Safety becomes critical in this context. So the real problem that we set out to address in this program is how can we assure that learning systems are safe and correct? Now, uh, assurance of safety critical systems is not a new problem, right? I mean, a hard problem, but not a new problem. There has sort of been a lot of work in that space, and there are both approaches from the communities that we all work with and also from the certification industry. What makes it unique and different for systems with learning? Um, and I'll submit a couple of these points for your consideration. There is, of course, a number of, fiendishly many hard problems, but here are a few. Um, so safety or assurance engineering basically starts with requirements. Um, Formal verification begins after specification. With machine learning, this is sort of one of the first problem one runs into, right? So at best, the specification is sort of an implied specification that says that the learner should basically do as what the training example suggests, right? If the inputs are similar to what was in the training set, then the output is expected to be similar. Well, try formalizing such a specification. Um, so that's sort of one aspect of problem in characterizing and providing assurance for machine learning systems. The other aspect here, uncertainty, again, dealing with uncertainty in systems is not unheard of, right? We deal with sensor noise. We do systems engineering where we make decisions under uncertainty all the time. What makes it challenging in this context is that the nature of uncertainty is poorly understood, right? It's uncharacterized. There may be a very well, characterized region of behavior for that learning component, but just around that, on the edges, there may be some undefined behaviors. So extremely difficult to deal with that in a systems context. Um, Opaqueness and complexity of implementation, right? So against our sort of classic notions of certification and assurance, so standards like DO 178B, they look at, if there's a particular piece of software that's deemed safety critical, then you're obligated to provide some assessment of coverage of, or basically design test cases that cover the full branching behavior of that software component. Well, there are no branches in a neural network. And so what does it mean to cover the behavior space of a neural network? So these are the sets. Now, learning and adaptation. So in some sense, all systems undergo evolution, right? But typically in sort of DoD deployed systems, the evolution sort of is the slower pace, and we basically uh, pursue an approach where the system is designed. We run through a series of V, and then the system is sort of blessed in some ways and allowed to be deployed. For these class systems that are using learning algorithm, there is an implicit expectation that we should be able to accelerate that cadence. We should be able to adopt the system, sometimes in a mission specific sense, sometimes even during the mission. Well, to enable that, we really need to sort of rethink how we do the assurance. The assurance cannot be thought of as an activity that we only do prior to deployment and then sort of forget about it or do sort of in a minimal sense, right? We really need to think about how we can make assurance as part of the system itself, how we sort of update and evolve our assurance arguments to go along with that. Okay, so that's talking about the challenges. Now, how are we thinking about this in the program? So our approach to these challenges is really a comprehensive assurance architecture and an assurance approach that reformulates these problem into these three sets of questions or challenges, if you will. First, how do we formulate assurance cases for systems that use machine learning? Second, how do we maximize coverage and derive evidence of correctness for machine learning based components? And third, how do we detect and ensure safety when operational conditions diverge? So let me just elaborate on that a bit. We start really sort of from thinking about really from the safety engineer's perspective. For a safety engineer, the assurance case is some of the natural speak in a sense, right? You start um, reasoning about the hazards in the system and what are the failures that contribute and lead towards those hazards. The failures may be because of variations in the environment, or failures may be related to the system and component themselves, right? And then the obligation of the safety engineer is to now look at all the mitigations that need to be provided to address the different sets of hazards. In the assurance case, is basically sort of a final product, an artifact that shows that the hazards have been thought through and the mitigations have been captured for these hazards and provided and corresponding evidences have been submitted for those. Now, the other question here is, well, how do we then, where do the evidence come from? So the evidence, to some extent, largely comes from sort of the classical systems engineering approaches, right? So these are things like formal verification, simulation, and even testing. Generally, the notion of assurance always deals in providing coverage of the system's behavior space. Now, this is with the full realization that for systems, autonomous systems, learning-enabled systems, coverage in an exhaustive sense is, of course, an impossible task. And so then our challenge is, well, how do we sort of intelligently cover this such that we are exercising some of the some of possibly some of the rare and hazardous scenarios. So this is sort of what we're looking in this area. And then the third part here is that there is sort of a notion of behavior space that we have well characterized, and within that region, if you're operating within that region, that we expect that the system is functioning normally. Question is, how do we sort of in a sense force the system to stay within that well characterized region? And that would entail a couple of things, right? We first need to be able to detect when we are going out of that well understood and well characterized behavior space. And then if we do end up going outside of that well understood behavior space, then how do we sort of steer it back into the system by providing sort of recovery and appropriate resilience mechanism? So that's sort of how we have framed this problem. In DARPA speak, these ends up being technical areas of the programs. And so we have three technical areas, the TA3, which is the assurance case. I will not belabor this too much. The TA1, this is what we call the design for assurance technical area. And this is looking at sort of the core classical systems engineering technique, but rethinking them, reforming them to some extent for learning algorithms. So what does it mean to do form verification for learning components or systems including learning components? And then the TA2, operate with assurance. So that's basically thinking about techniques that would basically incorporate at runtime. So this can span things like monitors and some of the safety wrappers that you'd put around the learning components. Okay, so that's just sort of a quick and high-level description of the program architecture. Let me now just give a shout out to our performer community in the program. We've been fortunate to be able to attract some of the best and brightest working in this space with us. And these are listed by the technical areas, but they contribute to all the areas in some ways. The Collins team that's led by Darren Coffer, and we have a very good group at Stanford, Clark Barrett, Michael Kokendorfer, and Marco Pramon working with us. HRL, Alexei Nogin, CMU, Andre Platzer works with them. Vanderbilt, Gabor Karsai, and he leads a group that includes Xenophon Kotsukas, who's doing some of the work on assurance monitoring, and Taylor Johnson doing formal verification work. Claire's group at UC Berkeley, Shankar and Sanjeev, they're working with Claire. And at Stanford, Dorsa works with them. Really some excellent work coming out of there. UPenn, in Supply, George Papas is on that team, Rajiv Allur, and a couple other people working with them. So these are our core TA 1 to 3 performers. There are other folks here, Galwa, led by Matt Clark, and Purdue Suresh Jagannathan works with them. SRI Susmit Shah, and Richard Murray's group at Caltech is working on the problem. And then we have, as I mentioned earlier, we have these 3 TA4 performers that are providing the platforms and challenge problems in the context of which we do the program evaluation. So that's sort of the program in a nutshell. Now, let me just articulate briefly where we are in the program, what kinds of technologies we are working on, and some of the accomplishments and results that I'll just summarize. So just from a technology map perspective, we actually have quite a broad portfolio with techniques spanning in quite a few different areas. On the TA1 side, as I said, this is the design time assurance TA. And here our work spans a couple different formal verification approaches that a variety of performers are working in the program. Some simulation-based approach. Here I'll show an example. Sanjeev is working on that problem, Sanjeev Seshia. Test synthesis, so this is looking at sort of the coverage problem. Both Berkeley and Collins group are working on that. Some of the monitoring techniques, monitor synthesis, so formally correct monitor synthesis. That's work at Kestrel. On the TA2 side, a large portion of the work is focused on assurance monitoring and a few different approaches revolving around conformal prediction, anomaly detection. So basically when the data has anomaly and it's not out of what you expect from it with respect to the training data set. Confidence estimation, that's a classical problem in neural network where the classification produce results, but the confidence on these results could be horribly off. And then on the TA2 resilience recovery, that's a key and important part. And here some work from Claire using game theoretic approaches, simplex architectures when detecting when things are not working right to switching to a different controller. It's from Collins. And then some of the contingency logic work that Collins is also working on. On the TA3 side, so this is actually building assurance cases and building assurance cases to link them with machine learning algorithms. A group that's affiliated with NASA Ames, SGT, that works on that problem. Then a couple other performers are building tools in that space and our platforms. So what I'm going to do is the next few charts is just show you examples, representative examples in a couple of these contexts. So the first one here, this is a representative of a class of verification approaches that we're building. This is just one of many, and it's looking at sort of subset of the problem. This one deals with verification in terms of input-output properties of neural networks. So when you're asking a question, if the input is bound by a certain set of constraints, can you assure that the output is also going to be bound or will satisfy certain properties? A representative benchmark problem that these approaches work with is the ACAS system. In just a few words about that, the ACAS system is basically sort of generating an advisory when there's a intruder aircraft into the airspace, generating advisories that allows your own aircraft to continue on its course or take evasive actions in certain form. Now, the classical implementation of this ACAS has been just using sort of a high dimensional lookup table. But the recent work funded through FAA is looking at neural network to replace that. Now, when you have a neural network doing this kind of advisory generation, then the natural question comes is that, if the intruder is in a certain orientation and approaching towards you with a certain direction and certain speed, can you be assured that the advisory, so here's an example. This is if the intruder is near and approaching from left, network will always advise strong right. The way this kinds of approaches are working, they take a specification like that along with the description of the network and translate it down to sort of in this case, an SMT representation. There are other folks who are just using recasting that as an LP problem and solving is using that tool. So these approaches have been successful sort of within this context. The scale, as you can imagine, is always a challenge here, but at least I think the current state for this is sort of in the order of tens of case kind of neural network, and that can be adequate when you use the neural network sort of in a control context with a limited sort of decision space. But clearly that is not sufficient when you're looking at sort of perception class problem. These kinds of techniques will not scale in that case. And there we're bringing in sort of different approaches. They combine sort of simulation and simulation-based verification. I'm going to show you one work from Sanjit Seshia's group that's actually addressing a very important problem, and that's sort of looking at using simulation to guide physical testing. So as we all realize, and I've seen it before as well, physical testing is important, but can be quite expensive. In fact, in some of the work that I was involved with at DARPA in the past, the just basically running and setting up these simulation experiments were inordinately expensive. And the number of tests you can get done in a day is just very few, right? And with all kinds of variation that you get. So the interesting issue here is how can you use simulation to prioritize testing in some ways. And the way Sanjit is doing this is basically setting up these kinds of experiments in simulation. So here sort of is a concrete example where what we want to understand is the autonomy behavior of this self-driving car, especially in a scenario like this where the car is trying to turn right, and then there's a pedestrian trying to cross the road at the same time. Now, for evaluating a scenario like this, there are many different parameters in this scenario, many different things that could vary, and you want to understand the behavior of the autonomy algorithm in with respect to all these variations, right? So here, it may matter where the AV started from, where the when did the pedestrian start related to the AV. If the pedestrian is going to hesitate, how long does he hesitate while the AV is interacting with him, and by the time he gets to an endpoint. Sanjit does this by constructing, what he has built is a probabilistic programming language that allows him to specify the simulation scenario not just as a point scenario, but rather a distribution of the entire sort of space of physical distribution of this object. So here, he's able to parameterize the starting position and the pedestrian's behavior with respect to when he starts, how long he hesitates, and so on and so forth. And now, once you have a specification like that, then you can start a variety of sampling techniques. You can do open loop sampling, just uniform sampling would be the basic one, but you can do importance sampling, or you can do closed loop sampling where you're observing the overall behavior been able to do these kinds of things. Now, uh, so once you do these kinds of simulation, then you get uh, basically you're characterizing these simulation runs with respect to how effective these runs are in terms of being able to satisfy the safety property. The safety property here is, of course, that you want the pedestrian to be a certain distance away from the AV always. And now you characterize these, and then basically you pick a set. So this is uh, not surprisingly different from the classical notions you have testing where you choose some test cases which are positive test cases, some that are negative, and some that are on the boundary. So he chooses a set of test cases from here, and then does physical and has done sort of physical experiments using these setup. Now, the good result here is that we see sort of a good concurrence between the simulation-based evaluation as well as physical testing evaluation. So the scenarios that have been demonstrated to be safe in simulation also turn out to be safe in physical experiment. But the important thing is that an approach like that can help now identify what are the key tests you should be running. Okay, let me just briefly and quickly talk about some work from the runtime assurance perspective. So this is a sort of again, classical problem in neural network sense where the performance of the learning algorithm is really dependent on how similar or disjoint the operational data, what you're encountering at operational time is with respect to what you're trained with. So here, the approach, this is Xenophon Kotsakos' work. And what they are doing is basically trying to build a mechanism to characterize how well the operational data is related to the training data set, and using what he calls a non-conformity measure. And the challenge here is, of course, that this kind of non-conformity measure for an operation time technique, that computation has to be done efficiently in real time. So some of the classical approaches that you'd use, like k-nearest neighbors and stuff, and try to characterize distance from the training data set, they're not scaling well, right? So instead what he has done is to train a neural network architecture in this case that can efficiently compute the NCM and how the NCM values are distributed with respect to the typicality. Here is just a video of the results. So some of the measures that are shown at the chart at the bottom, they show the p-value, that is the typicality of the data, and then an aggregated measure called the martingale that he computes that basically can be used now as an assurance measure. So in the first case, the training data and the operation data are very similar. So basically, we're just working in distribution. But in the second case, they introduce a divergence by introducing rain in the scenario. And in the case of rain, well, the learning algorithm obviously misperforms and ends into collision, but they are able to detect that with this p measure and the martingale. Okay, so that was just a brief sampling of some of the key technical approaches. Now, let me talk about the program evaluation, the challenge problems, and demonstration. So, for a program like mine, evaluation is an extremely difficult problem in a sense, because if the assurance is working, then basically nothing should happen, right? You should be able to mask out all the bads, right? And so the way we are trying to assess it is that we've engaged with these different challenge problem providers and have tasked them to construct some scenarios, some missions that you'd want to execute with that AV. And then within the context of that scenario, test the technologies by introducing variations in the scenarios. So let me just enumerate the few that we're working with. In case of TARDEC, this is I keep saying TARDEC, used to be known as TARDEC, now it's CCDC. But this is sort of a ground domain problem, specifically sort of in the DoD context where we are driving not in mainstream roads, but driving in sort of uncharacterized or unstructured terrain. And here we're using learning to be able to characterize whether terrain is drivable or an obstacle, and use the learning to provide hints to planner. So that's sort of one challenge problem. Another problem here is to be able to plan a path through complex terrain, and then safely navigate this waypoint path at high speeds over low friction surfaces. So several of our performers, HRL particularly, is working on the problems with Tardic. With Northrop Grumman, that's our underwater domain challenge problem. And here there are several interesting and DoD relevant challenges. One of the baseline ones is that we work with is um, tracking or tracing or characterizing an infrastructure while avoiding obstacles. So this is, think of it like an underwater vehicle tracking a pipeline underwater. And it needs to be able to do that. It needs to be able to cover the pipeline, and it needs to be able to avoid all the obstacles. In phase one, we look primarily sort of as a static obstacle. In phase two, we're looking at increasing the challenge in the scenario by making these dynamic obstacles. Another kind of problems that happen is typical in this context is that UUV might end up losing a fin, or may run into some sort of a hazard by virtue of the system itself. And you still need to be able to operate such a vehicle in a degraded condition. And then we're also doing scenarios where we try to conduct search and survey operation in a complex maritime environment. In the air domain context, so this is work with Boeing. Several interesting challenge problems here. So we started in our phase one just looking at ground navigation, so basically doing autonomous taxi. But in phase two, we're looking at sort of more landing and takeoff kinds of operations as well. Here in the from a autonomous takeoff perspective, then we're looking at, you're doing a takeoff decision, and if you end up running into an obstacle, or if it's not possible to finish your takeoff, how do you sort of when do you decide, how early do you make the decision, and when you want to abort takeoff? Okay, just wanted to show a demonstration. This was, in fact, Claire's work with Boeing at the end of phase one. Very interesting problem where we are actually operating this autonomous aircraft, conducting a runway taxi in an autonomous sense. And what happens when a unanticipated vehicle cross the runways? Now, the interesting part of this problem is that we're also trying to work sort of in a degraded condition. So basically, if your perception degrades, what you'll see in the demonstration is that there is a perception component that's both providing the ability for this aircraft to track the runway and also detect obstacles. So at some point, and we sort of artificially increase the degradation by introducing this kind of fog, and so you lose basically tracking at that point. And what you'd notice is that the vehicle reacts by stopping. Now, normally it would plan multiple trajectories, multiple possible different trajectories that are still safe and can be executed. Once that degradation goes away, then the vehicle can still continue operating safely. So that was a very exciting work that we were able to support through this program and participated in this demonstration. Okay, I think I'm running slightly over time, so let me just stop here with this set of concluding remarks and leave questions. Thank you.
Okay, great. Thank you, Sandeep, for a great talk. Are there questions for Sandeep?
I mean, I have a question, but I ask Sandeep a lot of questions, so maybe I can leave it till the discussion afterwards. If there's no other question, I'll ask my question, Sandeep.
Go ahead, Claire.
Okay, maybe I'll go ahead. So, Sandeep, we saw, a variety of different kind of application domains this morning, and then you presented the air, water, and ground scenarios. how is there a kind of tension in the program between wanting to have demonstrations that really kind of capture people's excitement and show off the technologies, but then on the other hand, you have to kind of keep it safe, right? So the performers, I mean, we know, working closely with Boeing, how important it is to have that fine line between demonstrating something, but really demonstrating it in a way that says sort of, wow, this wouldn't have worked if we didn't have this technology. So, I think of Lars's, years to get to the kind of tests and now flights that he's able to do. But how do you manage that tension? It must be challenging.
Yeah, that is actually, you bring out a very important question, right? So, I'll just sort of use the example that we just saw in the last slide, right? In some ways, well, one could say that the demo is not exciting enough, right? Because the aircraft just stopped, right? But on the other hand, that is actually quite a significant result, right? That you're able to do it with an aircraft at that scale and with all the safety concerns. From the program perspective, I had to sort of thread it from both sides, right? From a DARPA perspective, we want to push both our challenge problem provider as well as the performer community to sort of increase the challenge in the scenarios and make the demonstration more exciting. Whereas from the platform provider perspective, it's, these are sort of real safety hazards, right? You cannot operate an aircraft, and we're trying to do, in the next phase, we're trying to do sort of an in-air experiment, right? You would you would not do that without sort of the safety mitigations in place, right? So I think the way we try to manage this is basically that, certainly put more rules and constraints around the demonstration, right? So even in the van, the van was coming in the runway, but it was still pretty far off from a safety distancing point. So even if our assurance techniques or the safety kernel work that you had done would have failed, we would still not run into a real safety violation. So the short answer is that it is hard, right? And the approach that we take is basically just try to push both sides, right, while maintaining safety.
Yeah, no, I can see that. I think that's is exactly what's the right thing to do.